information retrieval to finance. And okay, so what is a Markov chain? A Markov chain is simply a connected belief network like this. So we've got a collection of variables, V1 through general through Vt. And the joint distribution is just given by some initial distribution V1 multiplied by the products of these transition probabilities. Okay, so what does the Markov mean? Well, Markov means that in general we could have a dependency of, say, V4 on all of the previous variables, V3, V2, V1. Right? This is this cascade structure that we saw in the first lecture. So the dropping of these links actually is what's called Markovian. In this particular sense, it means that Vt only depends upon its immediate predecessor, Vt minus 1, not on any preceding variables. So typically for time series analysis, we tend to order things in this forward direction of time. You don't have to do it that way, but it's kind of a natural way to do it. And as you know now, we can carry out margin inference, say, over a variable V3 or Vt in general, in linear time in the length of this chain, using message passing propagation. Now, one point of confusion, depending where your background is, you may have seen pictures a little bit like this to describe Markov chains. And this is actually looking a bit like a kind of belief network or some kind of graphical model. This has got nothing to do with the belief network or graphical model. Well, it does have something. There is a connection, but it's what this is a so-called state transition diagram. So here, what this means is that the variables V1, V2, V3, all of them, I'm going to assume have the same number of states. In this case, they're going to be discrete variables with 9 states each. And what this is, this thing here, is just a representation of P of Vt given Vt minus 1. So in other words, you could have, in this case, the Markov chain is defined by, let's say, state I given B t minus 1 is in state j, defined by this whole matrix. Right? So this would be represented by a 9 by 9 matrix. And so this, the first column would say, well, if we're in state 1, what's the distribution over the states? We will go to the next time step. And similarly, if we're in state 2, etc. Now, it could be that this matrix here, this state transition matrix, itself has some structure. And that can be represented by a state transition. So what this one, for example, is saying is that if you're in state 1, you can only go to state 2 and to state 8. What that would mean is if you're in state 1, you cannot go to state 1 again. You can go to state 2 with some probability, it might be 0.3. And you can't go to state 3. Or state 8, you can go maybe some probability 0.7. Those are only the 2 accessible states from state 1. Now, sometimes people will write, they'll do 0.3 and then do 0.7. They might write these probabilities down on this state transition diagram. Okay. So don't get too confused with this. This is a source of confusion potentially. So you'll often see, maybe in some literature, this reference to these is just a description of this. It's not the graphical model itself. Okay. Now, let's imagine we want to do we can try some fun things with Markov chains. So what's, say, the kind of shortest path algorithms and most probable paths, these kinds of things. I mean, these are kind of fun things you can do, right? So you could say, here's a state transition diagram. What's the shortest path from state 1 to state 7? Right, from state 1 to state 7, well, I can just go through to state 2. that would be the shortest one. There's no shorter here. On the other hand, you might say, what's the most probable path from state 1 to state 7? Now, if I just assume that all of these links have got uniform probability in the sense that basically if you go out, say, of state 1, you can go to state 2 with the same probability because you can go to state 8, in other words, a half in that case. Or if you're in state 2, you can go to state 3, 4, 5, 6, and 7 with equal probability. So that'll be 1 over 5. Because there are 1, 2, 3, 4, 5 possible states you can go to from state 2. I'm just going to assume that. I could write all these down. Okay? So if you're in state 9, you have to go with probability 1 to state 7. Okay. Now the most probable path, though, is this one. From 1 through to 8, 9 to 7. And why is that? Well, let's imagine you want to go. You want to go from 1 to state 2 to state 7. What's the probability of doing that? Here in state 1, what's the probability that you go to state 2? Half. It's a half, right? If you're in state 2, what's the probability of state 7? 1 over 5. So that path has got probability 1 in 10. And then if we go 1 to 8 to 9 to 7, we go from 1 to 8 with the probability half. What's the probability of 8 to 9? 1. So this one says the probability half. And this is much more probable than the first path. So there's, in general, there's a distinction between the most probable and the shortest path of the same necessarily. So, these kinds of problems you can imagine, they come up all kinds of places, right? You want to find shortest paths on graphs, or you want to get from A to B, Google Maps. How do you do this? What's the shortest way to get from A to B, given all these paths? What's the most probable routes could come from other areas of the site? So these are very, very common problems. And I'm going to show you one way to solve this. A little bit with the kind of dynamic programming ideas, message passing that we think about. Okay, let's try to solve the most probable path problem. So I want to find the path from say state A to state B in this Markov chain, and first of all I'm going to make an assumption that I know the length of the most probable path. We'll relax that. Okay. So let's say I know that it's a t length path. Okay, so I start at state A, I go to some state S2, and then I'll go up to t minus 1 states, and I'll end up at B. So t states later I'll end up at B. Okay. What's the most likely set of states, intervening states S2 to ST minus 1, which will make that path the most probable path, t length path. Okay. Obviously, I could define t minus 1 or t plus 1. I'm going to call it a t length. So I'm going to denote that A to B in t time steps. Well, I want to do the max over S2 to ST minus 1 of the path. And the path itself is a product of all of these transition probabilities, like we have here. Right? So it's going to be given that I start out in state A, whatever that is, I'm going to have then some transition to probability S. State S2, etc. with these intervening probabilities. And I'm going to end up with time step t in state B, given that I was at some prior state ST minus 1. Now we can use our sort of dynamic programming message passing intuition to simplify that calculation, because we don't want to do that exponential, there's an exponential number of states there that we have to search over. But we can distribute again this max operator, right? Because these are probabilities, so they're non-negative, so we're allowed to do that as before. It's a semi-ring structure. So we can distribute, say, there are different ways to do this. We could do the first one over S1. So where does S1 appear in this product. It only appears in the first term. So I could do the max over S1 there. And then what will that be? It'll be a function of whatever's left where S1 occurred. It's S state S2. Sorry, not S1. So S2 only occurs here, and when I've done that max, it'll be just a state of the variable S3. Whatever it is, because I've fixed A, and I've done the sum over S2, so it's only some function of the variable S3. And we'll represent that as a vector over however many states, and as many states in this vector as there are states in variable S3. Okay, and then similarly, I can carry on and say, well, where does S3 occur? Well, it occurs in this gamma of S3 and P of S4 given S3. It doesn't occur anymore, so then the maximum over S3. And in general, I can use messages gamma from a say time step t plus 1 as a function of future st plus 1 as a max of the incoming gamma and the transition probability. Now this looks very familiar to our message passing in the factor graph formulation, and if indeed we could write it down in exactly the same way. But here, because this is a singly non-branching connected structure, I don't need to worry about factor to variable and a variable to factor. I'll just do it in a one. I'll just do variable to variable message. And I'm just going to call them gamma here. There's no complexity arising from having to marry messages from branches. And we'll keep going until we get to the end time. The final answer is that the probability, the most likely, the value of the path which is most likely is given by just the final max from the last time step, given incoming message, given the final time step probability, given that you clamp it in state B. Okay, so that's the. I could also call that message from sort of time step t minus 1 to t when the final state t is clamped in state B. It's a notation you find. So this is nice, right? So now I've got this. I've computed this term, this most likely path, in the t-length path in linear time, so that's good. Now, imagine I I said assumed it was length t. Maybe it could be length t plus 1, maybe the most likely path. So I'd like to now calculate the most likely path for t plus 1 time steps. Okay, so I could start right from the beginning. Say, no, now I assume it's length t plus 1, and carry out that computation again. But of course what's going to happen is that those initial computations are all the same. So for the t plus 1 time step case, I'll carry out, defining gamma of S3, gamma of S4, they're exactly the same as they were for the t time step case. They don't change, right? So in other words, all I need to do is I can just go to get the t plus 1 case, I just use my previous t minus 1 to t, but now I don't clamp st in state B. I just carry out the new message where I clamp the next time to state B. So it's totally analogous to before, just that all these messages have now been defined. And now I'll get, again, the most likely t plus 1th path from A to state B. So this is nice. So what it means is that, as you can see now, this is just a, an order 1 operation here. So for order 1, if you like, or just the number of states actually of the variables S, I'm incrementally increasing my knowledge about the most likely path from state A to state B in t time steps. Okay. So I can keep going like this, and surely, if there are n variables in this network, I don't need to go more than n states. Because if I start doing that, I'm going to revisit. I'm doing more than n plus n more than n states. I'm going to revisit some states more than once, right? I'm going to revisit a state. And surely that cannot be the optimal thing to do. There's no way the optimal path is going to involve revisiting a variable that I've already visited. That's not possible because it will only decrease the probability. So what that means is that now I've got all the information I need to know from A to be in 2 time steps, to A to be in n time steps, which I could compute in linear time. Well, each of these operations took, let's say, if there were s states of the variable, took s states to compute, and they're going to be n variables, so it's going to be linear number of variables roughly, and it's going to be, I don't know, it's going to be roughly linear or worse quadratic enormous things. So. Okay, so now you've got this list of n path probabilities. And what you could do is say, well, which is the most likely of those probabilities? So you might say, well, it turns out number 37 is the most likely. So I can get to A to B in 37 time steps is the most likely path. Right? So that would then tell you that t equals 37 is the most likely path. And then all you have to need to do is to figure out what is that path. Now you know the maximum time step, well, you just need to backtrack. So you now know t star, the most likely time step. And because A to B and t star is given by this max over here of s t star minus 1, this is the definition of the message here, you know that the optimal state st star minus 1 is just given by whatever state maximized that probability, just the argmax of this term. Now similarly, you know the optimal state st star minus 1, so you can begin to backtrack again. So well, by the message definition, st star minus 2 then, this is the message, well it's just the argmax, whatever state st star minus 2 maximized this term, this message. And then you just backtrack to state S2 star, and then you're done. Okay, so you can see we have a forward propagation through to the end of the chain, maximum n time steps, and then we just need to find which time was actually corresponding to the most likely one, and then we find that and we backtrack from that point to get the actual state which maximizes the chain path. So you can, with most of these things, I mean, I will not go through them in lectures, but there's code. You can look at the demo code and read the book about where the demos are, what you call it. It's all there for you to examine. If you want to look at more details of how the code works, then just look at that as well, implementation to work. Okay, so that's kind of cool, right? So you can find, if somebody wanted to say, how do I get from A to B on a map, and I know all the road lengths or something like that, or maybe how do I do that? What's the most probable way to do it? It can be done this way. So there are some slight numerical problems with this. And the problem is that depending on how you define these things, these probabilities will typically, of course, be less than 1. Right, so let's say they're a half. Right? So these paths are, what's the probability, typically then of, let's say, a length n path. Let's say each transition probability is an order of 0.5. That means the path probability is actually itself going to be of the order 2 to the power minus n. Right, so that's very small. So we're going to get the actual value of the most likely path, or any path, is going to be order 2 to the minus n of that kind of idea. So it's exponentially small. So you're going to run out of bits on your computer to represent this. It's not possible to do that. So you're going to get overflow. On the flow. So depending on how you do it, you could get overflow if you renormalize things. So practically, we can't do it that way. We have to work with another numerical representation. So one way to do it is just to use logs, right? So, so we can kind of just say, well, and go back to this problem here and say, well, actually, I could take the log of this whole path probability. It's a positive number, so that's good. I take the log. And I could just take, the state which is going to, the log of the max is, well, because log is an increasing function, the state which maximizes the log is the same as the state which maximizes the function itself. So in other words, the max over x of some function of x is equal to the same state which maximizes the log vector x for, obviously, the positive end. So we can use that fact to say, well, we may as well then just work with log path probabilities, and that's handy, right? So you can say the log of this whole thing, this product will then, the log of the product is the sum of the logs, right? So you'll then want to find the most likely summed log path, right, rather than the product each time. And these logs will be okay, right? You know, log 0.5 is whatever, but it's going to scale roughly order n minus n log 2. That's going to be roughly the path log probability. So that's fine. That's just something which is scaling linearly. You know, we're not going to run out of, unless this chain is exponentially long, we're going to have no difficulties there representing those numbers. But all we would have to do then is that these messages, instead of having these products, we now have logs and sums. So we're going to have a log messages which are defined on the sums rather than these products. Otherwise, it's exactly the same. So if you're interested in that, you can look at the code how that works. So that's the most probable path. What about the shortest path? Well, let's imagine that your paths have got, say, some weights u. So maybe the state from st to st minus 1 to st, it's got some weight associated with it. It could be positive or negative, 0, doesn't matter. Okay, then I'll leave you to think about it a little bit, but if we define the transition probability to be this, the exponential of the minus of these edge probabilities, so these edge weights, then this basically, if we run the most likely path on this, it will correspond to finding that path with just the smallest sum u. It's equivalent to that. Simply because when you take the product of these paths, you get the exponential of the product of these things, the exponential of the product, and the exponent, you get the sum of the u's. Okay, because of the max, then this, if we've got a minus here, then we get the shortest summed path. Okay, so if you've then got Google Maps and your roads have got, say, times on them or distances or whatever it would be, and you want to find the shortest distance between A and B, shortest path, which is the shortest distance from A to B, you could use this algorithm. Okay, so this is kind of nice, and this algorithm works very generally. It's more general than Dijkstra's algorithm in classical Dijkstra's algorithm. There may be some subtle things to do with notation of complexities, I don't know, but Dijkstra's only works if the edge weights are positive, but this generally works both positive and negative. So I don't know what this algorithm is called, but it's something that I'm just trying to impress upon you that it's straightforward to derive by for yourselves these kinds of algorithms just based upon intuition and message passing and distributing operators over these products. That's the key insight. Now let's think more. So that's kind of fun, right? Markov chains. You can do. You can find shortest paths in maps, Google Maps, all this kind of stuff. That's kind of fun. I want to think about another aspect of Markov chains now, the equilibrium distribution. So we've got this chain. This one here. So imagine you're observing a fly. Okay, and this fly basically he starts out in, say, room 1. And he bounces around at random. He can go to room 2 or room 8. Okay, and then he jumps around at random, and let's say he goes to room 7. Right. And this is a bit of a boring Markov chain. This is sort of boring, but let's imagine you have a state transition, where you can just jump. Let's imagine there's no, you can just jump from one room to another room with some problem. Then let's say after, say 10 time steps, you see which room is the fly in. And maybe he's in room number 7. So 1 to 10, you say after 10 time steps, he was in the first experiment, he was in room 7. Then maybe I say, okay, let's run that experiment again. Start the fly out in room 1. 10 time steps later, where is he? You observe it and you see, well, actually this time he's in room 5. And you keep doing this, building up, counting, which room this flies in. But let's imagine that actually we do it for much longer than that, 10 time steps. So say 1 billion time steps. But let's make it a bit bigger. Let's say it's infinite. Okay. Infinite time steps later. You count where this fly is. So you make a histogram then over the 10 states. And you say, what is the relative frequency of occupancy of the fly in these states? And that's what I'm going to call the equilibrium distribution. Okay. It's where the fly will be, if you like, in the long run on average. So another way to think about this is that if I know the equilibrium distribution, I know that then the probability that I'm in any particular state, right? Then I can figure out, well, there's a self-consistency argument here that if, in general, if I'm in state, if I know the marginal distribution at time t minus 1, the probability at time t minus 1 in some state j, I know that. Then what's the probability what's the marginal distribution at time step t? Well, by definition, it's the joint distribution. So it's Bayes' rule, xt given xt minus 1 times by xt minus 1. Sum over xt minus 1, the states of xt minus 1. I'm just writing j there, the states of xt minus 1. So this is the definition of a marginal times t minus 1. Times t, given the marginal times t minus 1. Now, if I imagine that this equilibrium, this marginal distribution, is settled down, and after a while, the fly, where he's going to be, is not going to change. The marginal distribution, the equilibrium distribution, is not going to change anymore. After 100 time steps or 1 billion time steps, the occupancy probability of the rooms will not change anymore. It will be the same. Where he is, of course, at any one particular time step, will be not necessarily the same, but the probability that he's in any particular room will not change. So this means that we could write this down and say, this probability transition I could write as a matrix M. This is a 10 by 10 matrix, and say it's for 10 rooms. And then what that means is that PT, this is a vector with say 10 states, is equal to M times PT minus 1, which is indeed the same as so this first one is saying that PT, this vector, right? There are 10 states of this vector is equal to M times by P t minus 1. So this is a matrix, and this is a vector. Okay. That's equal to M, well, Pt minus 1 is equal to M times by P t minus 2. So in general, this is M squared. So it's equal to M to the power t minus 1 times by P. Okay, so this is the matrix multiplied by itself t minus 1 times. So if we keep going, we can then say, well, at times of infinity, we can figure out what, for some given initial state P1, we will end up with some infinite equilibrium distribution. P is infinity. And similarly, by self-consistency, that whatever that is, we can look for P infinity of t. We can just, that will appear here on the left and here on the right. So in other words, P infinity is equal to M P infinity, if it doesn't change. So well, there are some subtleties between the equilibrium and the stationary distribution, which I'm not going to go into. Okay, so in matrix algebra, what this means is the equilibrium distribution, station distribution, I should probably more correctly call it, is equal to the eigenvector of unit eigenvalue of the matrix there. So you might say, why is it, how do you know that such an eigenvector exists? And it does. It's a fundamental theorem of Markov Chain that an eigenvector of eigenvalue 1 always exists. It just comes from the fact that this M column something 1. Right? So you can prove it. Maybe you would like to prove it at some point in your history. If you do undergrad maths, this is the thing that you have to do the first week in the Markov Chain course. It's a fundamental theorem. Okay, so let's see this thing. So here is a Markov chain of 10 variables. So you don't see it very well, but here's there's a 10 by 10 matrix. Got to sum n. You'll see that the columns sum to 1. I just made a random matrix whose columns sum to 1. Okay, so this is given. It's going to have 10 states, just a random matrix M. This column P just normalizes the columns to sum to 1. And then similarly, I'm going to start now with some initial state X. This is going to be the equilibrium distribution. So I'm going to assume that we start out with some equilibrium distribution, which is just some random distribution. And then at each time step, I'm going to say X is equal to M times by X. Okay. And maybe let's do another thing. Let's say we start out in room 1 with fly. Say X is equal to 0 is. And we start out in room 1 with certainty. Okay. So where will I be? What's the distribution of rooms I will be in at time step 2? Is M times by X. Right. That's the occupancy probability at time step 2. Then similarly at time step 3 will be M times by that X, etc. We keep building it up like that. So these are all random things, but so this is where we are at time step 1. We're sure in room 1, right? This is the probability here. At time step 2, for this Markov chain, this is the occupancy probability. Okay, so we've now this doesn't correspond to the example I was showing before with it's a different one. This is a random matrix. Time step 3, time step 4, 5. Okay. So the thing to observe there was that the first couple were a little bit different, but after the third stage, they were all very, very similar. See that again? It's the same to me. Surprisingly. I don't know why. Should it be the same? Can't be the same. Very, very unlucky today. Is that the same?
Not quite.
Okay, that's good. Sorry, I need to pay attention real. But you get the idea, right? So this thing converges very quickly to the equilibrium distribution. But that's good. In fact, the convergence for a randomly constructed matrix will be exponentially fast. Just related to the ratio of the two leading eigenvalues of this matrix M. Okay, so you get the idea, right? So one way to compute this equilibrium distribution, the eigenvector with unique eigenvalue will be just to repeatedly multiply, starting from some state. And you can do this experiment if you like, but it doesn't matter what state I start from, typically, for a random matrix. I mean, there are some cases where it does matter which state I start from. In these cases, there is no, formally speaking, equilibrium distribution, which is the distinction in Markov Chain theory. But for the cases I want to assume here, it doesn't matter which state you start from, we will always end up in the same equilibrium distribution. Okay, so you might think, well, that's interesting, but it's all a bit esoteric. But let's think of an application of something like this. Let's say that instead of flies, let's say we have websites. Okay, so let's say we make a matrix A ij elements, which is 1 if there's, say, a link from website I to website J to website I. Okay, otherwise it's 0. And then from this binary matrix is going to be pretty big, right? It's going to be a few billion by a few billion, or I don't know, matrix. I'm going to define a Markov chain. So I need to make the columns sum to 1 in the Markov chain. I should warn you, the statisticians like to have rows sum to 1 for some bizarre reason, which is really weird because it means they have to do matrix multiplication on the right rather than on the left, which is just perverse, but anyway. I define it this way. So now, let's imagine we could find the equilibrium distribution of this matrix. So what does that mean? You know, the interpretation would be that you start out at some web page, okay, and then you jump at random to the accessible web pages from that web page, those which will have links to other web pages, right? And then you get to another random web page, and you jump again with uniform probability to the accessible web pages from that web page, and you keep going. And then, you know, after essentially an infinite amount of time, you assess what's the probability of occupancy, of visitation of each website. So you might think, you know, for a very popular website, because lots of people are linking to it there, you keep revisiting that website, right? As you're bouncing around at random, surfing at random. Whereas in a not very popular website, obviously one which is kind of, you know, it's not very heavily linked to, you kind of, it's a dead end maybe, or you don't visit it very often because people are not linking to it very much. Okay, so that's so then the idea is that you could say, let's imagine you want to make your, you know, my first web search engine would work as follows. You basically go to every website, let's say there are a billion websites. You look at the words on each website. You know, there'll be a word dog, cat, whatever, pig or something. And you list them down. So you say, you know, website number 1, and let's say, first of all, maybe you list all the words in your dictionary. Okay, so you have this huge, long vector, right? Maybe several billion words or entries in this dictionary. You say website number 1 contains the word dog and you know, food. Okay. And you do the same for website 2. You know, this has the word cat food, etc. Right? So you make this. You know, you crawl around the web, making this list. Okay. And now somebody says, I want to find out something about cat food. So they search for cat food. Right? So what do you do? Well, you say, you better first of all find a web page which is got something about cat food on it, right? Otherwise it's pointless. So you say, okay, I need a cat and I need food. And you scan across this thing to find which websites contain the word cat and food. There might be more than one. It might be websites, in this case, number 2 and number 30. But these are your two candidate websites, web pages, because they both contain the word cat and food. And maybe there are many more. There might be 1,000 such websites, right? So what do you do? How do you present these to the user who's asked for this, to the search? Well, you could rank them according to their equilibrium probability. So you could say, website 2, yeah, but that's rubbish because it has a very low probability of being visited by random bouncing around. So what that means is that nobody cares about website number 2. It's somehow not important. But website number 30 maybe has a much higher visitation probability. So you can then present these web pages just ranked by their equilibrium probability. And that's PageRank. That's the first Google algorithm to search. It's very, 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 very simple. It's back at the envelope. Stop. And they were not the first people to think about this. It's not a new concept at all. But I guess they were the first to implement it on a grand scale. So, but they understood the theory of Markov chains, right? This is and if you have to do some bells and tweaking to get this, get this actually to work in practice, you'll find that some of these probabilities are very small, and you have to do some kind of some parts of the web are just not kind of like dead ends, so you have to inflate these negative or these zero probabilities with some small probability, and then renormalize, and then and then run out of now. So for those who've done linear algebra, you will know that the formal complexity of computing the eigenvalue is cubic, and the number of and the size of the matrix. So that may not sound too bad, but if you've got literally a billion, this matrix is a billion, right? 5 billion. That's a lot, right? Cubic is huge. So there's no way you can do this exactly. Even Google cannot do this exactly. It's impossible to compute the eigenvalue exactly. So what do? They don't go into MATLAB and say, compute for me the leading eigenvalue. It's a principal eigenvalue. It doesn't work like that. But they can do this repeated multiplication. Because they start with, they make some guess, and then just repeatedly multiply that, like we did before, as you saw, that will rapidly converge, unless you're very unlucky, to the equilibrium distribution. And that's what they do. But they just overnight, they just run their matrix multiplication, their few billion by a few billion matrix, they multiply it with some random initial vector. And that's the PageRank. And that's what used to happen overnight. You used to do it overnight, run it, and next day you get a new PageRank, a score for your web page. Okay, so that's one practical application. Okay, so now we're gonna move on to more sophisticated things. So I'll just try to show you can do some quite funky things with the concepts of singly connected variables and message passing. And now I'm going to do even more funky things with singly connected graphs. So let's look at the next step up from the Markov model, which is the hidden Markov model. This is a very popular model in time series, and it's used in all kinds of communities, from statistics, bioinformatics, computer science. Engineering is a major place, tracking. So your speech, all the speech recognition in your phone is done with this thing. All of your not completely true what I say. You shouldn't take things that I say with a pinch of salt, but by and large, it's true. You know, tracking of people, bags, is that bag being left? How do you track that person? How do you know where the football is on the pitch? And all these kind of things. How is that done? It's done with this, all of this stuff, all tracking. How do you do that? Music denoising, it's all done with this. This is probably the most popular used graphical model of them all. So it's extremely important. How do you do gene sequencing? Done with this. Okay. Super, super, super important. Okay, so what the heck is it? Well, it's a singly connected leaf network. These V's are going to be observed states, observed variables. So we will know V stands for visible because I'll know the state of it. H stands for hidden. I will not know the state of these things. Okay, so I'm going to assume that we're going to be in discrete variables just for simplicity here. And I use this notation. So V1 through to Vt, this is MATLAB style notation. V1 colon T. Right? And similarly, H1 through to Ht. So the joint distribution V1, V or V and H is given by this initial term VH1, VV1 and H1, then the products of this Markov transition. So if you like, it's jointly Markovian over H. That's another way to view this. At least they've got special terms though. So this is called the transition distribution. This is called the emission distribution. And we'll have some initial distribution here at H1. So let me give you maybe another example. Why is this model important? Just imagine that you want to predict the weather. The weather is forecast with this model. So what you could do is say, well, I know something about the physics of weather, right? So maybe there's some kind of complicated equations which describe how, if I know the pressure, how things are going to move. Right? So these are the Navier-Stokes equations in physics. Right? You could write those down. If we knew, what we could do is we take the planet, and we could kind of partition the atmosphere into segments. Maybe this is a two-dimensional representation, but we could make kind of cubes here. Spheroidal cubes, like in the atmosphere, right, going up to some height. And if we knew the pressure in each of these cubes, we could use a discretized Navier-Stokes equation to predict what will be the pressure at the next time step. It's a deterministic known system. Okay. Of course, there is some, difficulties to do with the discretization level here. I believe that these now are about 5 kilometer grids or something like that, 5 by 5 by 5 these days. I think they can do that. I mean, so the number of states over this thing is huge for the planet. It's, I don't know, it would be billions. It used to be 125, I think, or something like that. I thought there was something in the news recently. This is like 20 years ago. We had this big storm in the UK, and I think it's anyway 6 times. It's 6 to the power 3 more cubes now than we had in 1987. So whatever, it's about 200 years. Anyway, there's a huge number of them, right? So what you could say then is that, well, I'll call this H. So H will be. I'll enumerate each of these cells. I'll call this cell number 1, number 2, number 3, number 4, 5, 6, up to however many, say a million. And then I can write down the physics of Navier-Stokes. So this vector H, if I know the states of all H, What would Navier-Stokes tell me would be the state of the next time step? Because that's physics, you know, it's deterministic. Right? It's all, that's what. It's all just deterministic. Classical physics is just, if I know what's going on now, and you assume the states of motion, you know what's going to happen next. That's what it's all about. These are laws of physics. And actually, all of these laws of physics can be written down as second-order differential equations, which can be translated into second-order difference equation approximation, which could be, if you want, to be represented either as a second-order difference equation, or I could, just take it for me, I could represent them as a first-order equation in some extended state space. Okay, but by and large, you get the idea, right? Some deterministic. And you could say, well, you know, I will maybe, because there's approximations there, you know, and the physics is not completely right, and maybe I don't know exactly the state of what's going on in that thing. Maybe I really have a probability of, you know, the state transition for this whole thing. How would that really transition? Okay, so that's the good side. If you knew what was going on, and if you knew that, you might say, well, look, you know, the problem is I don't actually know what's going on there. I can only measure certain quantities. Like, for example, I can measure the pressure at the Earth's surface, right? Which might be some kind of summed weight of the column pressure or the column density at this particular location. So I can maybe, what I can observe here is, say, the sum of the h's, for example, or some function of the h's at particular locations on the Earth's surface. I cannot directly observe h, or maybe I know some weather balloon went up here and I know a couple of the h's. I know something about it, but I don't know everything. But if I knew what the h's were, I would know how to measure, say, the surface pressure here. It's just some known function again of h. It's specified that. Right? And again, I'll write a probability down because maybe it's only measurable, there is instrumentation error, etc. So that's the idea. Then, you know, you could say, I could write that down here and say, well, this h to h is representing the physics of the world. Okay, and this is just h to v, it's just representing my observations of the world. Then what I'll do is say, I actually observe these things here, v1, vt minus 1 up to vt. I know what they are. I measure those surface pressures. I want to predict what is going to go on with vt plus 1. What's going to be the surface pressure tomorrow? And that's an inferential problem. We need to infer the state of ht, to predict ht plus 1, and then get the marginal for vt plus 1, conditioned upon given the observations of the time step t. Okay. So you get the idea, this kind of thing. That's why we had, you know, this concept of hidden or latent variables. We're not able to measure them, but they are critical for the model. They encode our knowledge and understanding of the way the system works, but we are still, nevertheless, not able to directly observe. And that's why, you know, these are so ubiquitous, because clearly, you know, all of science is representable in that way. All the laws of, you know, physics, they're all in this form. All temporal, you know, first or second order differential equations, which are all representable in this way. So the kind of quantities that we are wanting to compute, they've got some particular terminologies. So one is called filtering, which means we want to infer what the state of h is, given all current, all states of the observations up to the current time. So in other words, what is the marginal distribution ht given v1 to t? Smoothing is to infer ht given past and future observations. So you might say, you know, I want to look back and figure out, given my future information, what actually happened, what's the marginal state distribution. The Viterbi is just that joint path which maximized hidden regulations, the joint latent hidden path. So I have to apologize with this terminology. It's from the engineering community. It's awful. And maybe I should have tried to change it a little bit myself, but it's such a entrenched, ingrained terminology, it's kind of hard to change. So Viterbi, he's a chap who, this is, they use this thing a lot in mobile phones for speech recognition. So Viterbi is he's one of the Qualcomm guys in the States, and he's this mobile phone guy. Qualcomm, something like that. It's a big mobile phone. So he's like, there was their lead engineer, basically, so to do speech recognition. So fortunately, it got named after him, which I think is a bit of a shame. Anyway, here we are. So how do you carry out these inferences? How do you predict weather? How do you predict the stock market? It's the same kind of thing. How do you do all the kind of things? Well, it's just inference in a singly connected structure. So it's easy, right? It's super easy. All of this. You already know how to do it. I don't have to tell you anything. Just run message passing. You already know the output. So you're done. So there are many ways to do this. One is to write down a factor graph, and we'll do that because that's what we were doing. So what's the factor graph for this? HMM has got this form to it, and then you've got, it's a branching factor graph. It's a little bit non-branching really because these are actually observed. So you could absorb these fixed potentials into any of these factors here. It's really just a chain. It depends how you wish to do it. So you don't even need to use the classical factor graph algorithm. You could just use the variable to variable version of it. And then you're done. I'm going to give you an example now of this thing. Another example. Okay, so you're at home and it's night time and you're in bed trying to sleep. And then you're under the duvet and you're woken up because you can hear something downstairs. There's some kind of noise in the kitchen. So you think, oh gosh, I have a burglar in the kitchen. Well, you know though the layout of your kitchen. So let's say that you say your kitchen is a 5 by 5, so 25 meters layout, and you know that because the floorboard structure, you know that the probability, say if the burglar is here, the probability of the floorboard creaking is quite high. But if the burglar is here, the probability of the floorboard creaks is quite low. Similarly, you might say, because you know the layout of the kitchen, the probability that if the burglar is here, of him bumping into an object or a table or a chair or something in the dark is high. Otherwise, it's low. So this is kind of your knowledge of your kitchen. And then the idea is that as you're listening to this sequence of creaks and bumps from downstairs, and given the knowledge of your kitchen, and as an assumption, say that the burglar doesn't move more than say 1 square at a time, so that you want to infer where you think he is. So if you were kind of smart enough, and you'd probably get an idea where he could be at any one time. So those are the problems that we're going to look at with filtering, smoothing, and Viterbi. So we've got, in this case, we use a HMM. H is going to have 25 states, it's discrete, each of the 25 positions and where the burglar could be. I'm going to have 4 states for the observation. So state 1 would be, say, no creak, no bump, 2, creak, no bump, 3, no creak, no bump, 4, say, creak and bump. But maybe we can assume that these probabilities of creaks and bumps happen independently. So I can define then, say, some joint probability over creak and bump given a particular position, which is the product of the creak and bump probabilities. So here we are. Here is, I never get this to work around, but anyway, let's say that this means here that the left is going to represent, say, creek, and the right is going to represent bump. So you observe creek and bump at time step 1. So, you know, you think based upon your knowledge, you know, this is filtering this one here. Where could the burglar be? So black is low probability, white is high probability. So you think, well, it's creek and bump, so you know, it could be in these locations here. Then you hear, say, a bump alone, the second time step, bump alone again, etc. And as you can see, your understanding of where you think the burglar could be is concentrating down to a smaller number of states typically. And such that by the time step, you're pretty confident the burglar is here. It could be there with some small probability. Okay, so that's the process of filtering. As you're going on, you're using the fact that, you know, so at this time step now, you know where the burglar, you know all the past information about creeks and bumps, and you use that to estimate, understand the margin, as much as you can about the marginal distribution condition on that information. Okay. So smoothing means that you come the next, let's say the next morning the police come, and you tell the police everything that you observed. Right, all this sequence of creeks and bumps, and the police say, according to us, well, based on what you told us, at time step number 5, our understanding as to where the burglar was at that time is given by this. So bearing in mind both what you observed in the past and in the future, that's probably at time step number 5. That's where he was likely to be. So this is what they call smoothing. Not very helpful. Now this one here, this is the Viterbi. This is the most probable path. So the police say the single most likely trajectory the burglar took through your kitchen floor, based upon all the things that you told us, this is the path he was likely to, most likely to take. That's the Viterbi path. Okay. And the one at the bottom is just actually what he did. No, they don't necessarily have to be the same. I think they're a little bit different. Okay. So that's that. So you can run the demo. Maybe I don't run the demo now for you, but you can run it. So here's another example. Now we're going to do typing. Right. So let's imagine we want to make a spell checking mechanism. Let's say H is going to represent the letter that you intended to type. Let's say there were just A through to Z and maybe the space bar, something like that. So the 27 characters that you could have done. V is going to represent the actual character that you type. So in this case, there are going to be as many, the state space is going to be the same. So the hidden variable is the intended key that you need to type, and V is the actual key that you typed. So you've got a little bit stubby fingers, so you kind of, well, maybe not stubby, but you press the wrong key. It's quite probable that you press the wrong key. So if actually you wanted to type Q, there's a high probability, the highest probability is indeed you typed Q. That's good. It's not totally random, but there's a reasonable probability that you typed W. Right, and whatever that is. I mean, it's a QWERTY keyboard, so whatever is should be A. So A should have a high probability. Okay, so if you look at the QWERTY keyboard, this is just the high probability. This is expressing the neighbor property on the QWERTY keyboard. And this here, this is just the letter-to-letter transition frequency for the English language. So if you are in a queue, this way, the wrong way around, but it has to, yeah, that's right. The Q has to go to a U. It just so happens in English, but if you're in say a T, you could go to a space, or you could go to whatever that's H with some high probability. I mean, you don't see the colours very well yet, but these are the you get the idea. You can get this from looking at just books and stuff like that. All right, so now what you can do is say, well, somebody's typed a sequence like that. What the heck did they mean to type? Right, so this is an inference point. So this is our observed V. And then we could say, what is the most likely hidden path, the Viterbi path for that? It turns out actually it's not, if you do that, it's not a word. It could happen. It's just, the most likely path will probably be the same word itself. So what you can do is you not just find the most likely path, but you say find the most likely 100 paths, or it's most likely, the second most likely, the third most likely, all the way down, until you find the first path, which is a word in the English language. And then you could say, well, I'll output that as my guess for what the actual user intended to type. Can you see what it's likely to be in this case?
Learning.
Learning, very good. But this is quite an easy one, actually. There are much more difficult examples where it's not so easy. So yeah, I wouldn't run the demo. You can run the demo yourselves. So I'm not going to.
Who needs to Markov when there's conduct to control you? It's just words.
So this is it's the 153rd most likely path, actually. So this is running Viterbi, going up. This is a less and less probable path, so more and more probable path. This is so the most probable one is actually KDAR space IG. And none of those were English words until we got the 153rd, which was the word learning. Okay, so you can see that this is kind of fun, right? You can do. I mean, if you type that into your your standard spell checker, there's no chance you will never get it. It doesn't work. So you could make much more powerful. You could almost like type pretty slappy, right? And then you still figure it out. But it takes a while. You see, it's not super. It's just like that, but it's not the fastest. Okay, so yeah. So I just wanted to say, give you another couple of ideas for where these kinds of things are used. You could say, let's imagine that you want to do what's called tagging, I think they call it. So let's say you have a sentence like the dog sat on the mat. I always get this wrong, but this is a well, that's the verb. That's a noun, right? That one I know. This is the verb. That's a noun. Is it preposition or no?
Article.
Article. Thank you.
Article.
Article. Is that a preposition? Yeah. Okay. So, all right. So I don't know how many of these things there are. There might be, say, 20 of word categories of words. It's useful sometimes to know. If you do, say, search queries, something like that. Is the word actually, maybe we want to disambiguate. So maybe some words are, this is not a good example, but they're ambiguous. Some words could be either, trying to think of an example. Fly, right? Fly sat on the mat. And then fly could be a noun, or it could be a verb, principle. But what you could do, you could say, well, I'll try to use the context of the sentence to disambiguate what fly is. I want to understand what the computer to tell me from this sentence whether or not fly is a noun or a verb in this context. So what you could do is say, well, I will have in the later states H1, H2. In this case, up to 1, 2, 3, 4, 5, 6, to H6. These will be the category of the word. So let's say there are 20 types, a noun, verb, etc., preposition. And I will observe the actual word. So this is the word 1, word 2, 3. So, for example, if the word is, if it's a, yeah, so if this is a verb, what's the probability distribution over words for verbs? Right, so dog will have 0 probability. Fly will have some probability. This will be very small values, but it will be non-zero, right, etc. Now, for all the words I have in my dictionary. Similarly, if this were a noun, I'd have another emission distribution. Fly would also be non-zero in that. Okay. And then what I do is I write down from my knowledge of what linguists tell me. Let's say somebody by hand has annotated a whole set of sentences, and then from that they would say, okay. So somebody told me actually that this was a hand annotated thing, and then maybe I have many such hand annotated sequences, and then I can figure out what the probability is of an article transitioning to a noun. I can write down the transition matrix, right? So then I know this, and I know this just from the English language. And now I observe, the fly sat on the mat, and I can infer then what's the most likely category for all of them, but also for that one. And in this case, he will say, well, it's a noun, because you don't have verb. It doesn't happen. So that's the only explanation possible. So you can, imagine how you can use these kinds of things to then, solve these sort of simple kinds of. Okay, so that's that. Now for Friday, just look on the Moodle page for this week's exercises. It'll be me this Friday actually. So Chris is away this week. So I'll see you at 9 o'clock as usual. So do crack on with the exercise and the assignment.